Perfect. Hi, everyone. So we are here with Nicolas Cuny, who is doing his postdoc at Université de Genève. And he's going to talk about modeling of the rheology of a pressurized blood vessel. So Nicolas, can you tell us a bit about why you did this postdoc and tell us a bit more about that now that we are registering the whole session? And after that, you can start. And are you okay also that everyone can ask you a question during your presentation?
Yeah, I was about to say it. Yeah, you
Okay.
can interrupt me.
Perfect.
You need.
So anyone, if you have a question, don't hesitate even to raise your hand or write it on the chat, and I'll ask the question to Nicolas, or you can see it right away. Nicolas, you can share your slide, and you can also start to discuss a bit about yourself, and voila.
Yeah, so do you
Perfect.
see my slide?
Yeah,
No?
perfect.
Okay. Yeah, okay. So should I start?
Yeah.
Yeah. So yeah, hi everyone. So I'm Nicolas Cuny. I'm glad to be here today with you to have this opportunity to present you a little bit of my work. And I thank for that Leonard and Michel for organizing this survey and inviting me. So maybe before I go too much into my presentation, so yes, I did a PhD in France, in Grenoble, more about rheology of passive material, of soft materials, mainly theoretic PhD. And after that, yeah, I had to find some postdoc, and I'm from this part of the France, so I was looking for something not too far from my home, and when I find this postdoc really by chance, I didn't know anything about biophysics before, and the subject on the kind of stuff that was doing Guillaume Salbreux, the PI for which I'm working now, were quite interesting. So I moved to that, and I have to say that I'm quite happy to move to biophysics. I am doing almost the same thing that during PhD. I'm using the same mathematical tool, the same kind of modeling, but for systems that for me are much more interesting than polymers or suspensions or stuff like that. So yes, is it okay as a presentation?
Yeah,
Should I?
Thank you. That's perfect. You can for sure.
Go ahead?
Thank you. Perfect.
Okay, so yes, I'm now postdoc for now 2 years. I'm starting or at the middle of my third year of postdoc at the University of Geneva in the group of Guillaume Salbreux. And so I'm working on the mechanics of biological tissue in my postdoc. And today, for the purpose of this guide to rheology seminar, I chose to present you one of the projects that I'm working on that is the closest related to rheology. So that is a project aiming at modeling the rheology of a pressurized blood vessel. So before that, let me give you some introduction about why and how people are looking at rheology for biological system, and why and how we try to model such kind of system. Okay. So, as I said, I started my PhD really on some classical material, passive material, soft dense suspension, that are some complex materials that are made of a lot of deformable particles that can interact by a contact interaction, for example, the simplest way you can think, and that are suspending in a Newtonian fluid. And the purpose of my thesis was to develop some kind of derivation to get some continuous description of this complex material at the mesoscopic scale, so the scale of a few particles, in a way to be able to model, to study the rheology of this material, but keeping some track of what is happening at the microscopic level of the particles. So I did that for 3 years, and after that I moved to Geneva, and as I said, I was quite ignorant about biophysics. I was naively thinking that biology and the physics were really two different worlds that were not able to communicate, that can't work on the same topics. That was quite different, but actually I realized by doing this postdoc that there is a lot of interesting things for fascinating. Even for a theorist, there is a lot of things to do, because at the end, okay, it starts again. Okay. So when you think about the biological tissue, so yes, there is mainly the biology, how chemical reaction, how protein interact one with another to give some behavior to the tissue, and this is mainly not the kind of physics that I like. But when you take the tissue as a whole, it's almost always has some mechanical function, and it's doing some quite important mechanical stuff. If you think about development, for example, the tissue has to deform in a really precise sequence of shape in a way to generate the organs and to end up with the full working organism. For example, you have here some video, some movie of sea urchin embryo. So it's some other project I'm working with a biologist. And you see that at some point, this really early in the developmental stage of sea urchin, the tissue is deforming and kind of creating some tube inside of it that is going to become the gut of the animal. So it's really some precise self-deformation that the tissue has to perform, and to understand that and to model that, to precise mechanical or rheological description of the tissue. And even after, when the full organism is made, is working, almost all organs have some mechanical function. If you think about a blood vessel, for example, it has to maintain the blood inside of it. Of course, it has to keep some radius in a way to control the flow of the blood inside the vessel, and so on. And when you look at the deformation it is submitted to, it is really rich. You have some shear from the flow, you have some stretch, and the kind of deformation he is feeling can really be complex. You have some oscillatory behavior, of course, of the pressure, but depending on which kind of vessel you are looking at, the fluctuation can be more or less important. The mean average can be more or less important. So it's really submitted to some rich mechanical environment. And if you want to understand how this is working, you have to kind of model it just like we are doing for whatever material. No, not the kind of problem I was saying that for inert material, and people started looking for studying the rheology of biological tissue. So there I would like to give you some kind of, it's not an extensive overview of what people are doing, but some kind of example of how people are doing rheology in biological tissue. So you can try to get some in vivo measurements, in vivo rheological measurements. It's something that we did for the sea urchin project that I just talked about a little before. So here you see it's kind of a funny experiment that our collaborators did. You have the sea urchin embryo there, and they just put some micropipette inside of it and apply some pressure inside the embryo, and you see just like a balloon, the embryo is inflating. And knowing the inflation with respect to the pressure that you apply, you kind of get the Young modulus of the tissue. So that's a kind of really simple rheological measurement you can do in vivo. But in most of the system, it's a little bit difficult to have some in vivo measurements. You can't put a tissue in a rheometer like you want, so you can perturb the system doing like that. So in general, people move to in vitro rheology. So here you have some kind of experience. You have some cells in a channel, and they divide and they flow just as a liquid, and they flow around some cylindrical obstacle that you have here. So for those that are familiar with foam rheology, it's really some classical kind of flow experiment that the people do in foam, and they look at it a lot. And the people that did it for tissue are actually from foam rheology. It's mainly François Graner and people like that that look at that, but for tissue. So you see some kind of in vitro rheology that you can do. But sometimes you have to really look at the organ in itself, and organ can be a complex thing. So people started setting up some experiments of organ on chip, so they reproduce the tissue that they want to study, but in a rheological setup, in order to do some deformation, to apply some controlled deformation to the tissue. So there you see they managed to build some double layer tissue with a layer of epithelium that is like the skin, and the layer of endothelium that is like blood vessel tissue, and that is kind of reproducing the lung, for example. And after that, you can stretch it. So you have some system by doing some vacuum in there. You see, you stretch the tissue and look at what is the response of the tissue to this deformation. So there is really a lot of work that is done experimentally to start to study the mechanical properties, biological properties of tissue. And just as for on the theoretical parts, for people that want to model that, just as any material, it's just like what I did in thesis. You go at the mesoscopic scale and try to give some continuous description of the tissue, relating the stress tensor to the deformation tensor to get some constitutive law for that. And what is important is also to keep track of the microscopic level, just as I did in my thesis. On the microscopic level for tissue, the level of biology is the level of cell. And cells are doing a lot of things. You have a cytoskeleton that can generate stresses inside the tissue. They can communicate together, and those kind of behavior of the cells are influencing the overall rheology of the tissue. So it's important to be able to derive some continuous description, of course, but taking into account the biology of the system. Because at the end, for example, where you are applying a drug, you are going to change the biology, and the biology is to change the mechanics, but you are not, for example, acting directly on the mechanic of a tissue. So it's really important to have some view of some input for the biology in this kind of model. So in this talk, I'm going to show you a little bit how we construct such a model for one precise example. But before moving to that, we would like to show you what are the key elements you have to take into account to describe a biological tissue, to describe the biology. So the first one is not a biological element, actually. It's really the geometry. A biological tissue, it's thin in one direction, so it's like a 2D material. It's not a bulk, like what we are doing in most of the rheology. And it can also have some complex geometry with some curved shape. So we have to take that into account in most of the case. But this is not so original. You have some shell model with a passive material. It's not something that is proper to the biological system. What is really original for biological tissue is that, as I said, they can self-generate stresses. It's what we call active matter. They are able to extract energy from their environment to generate stresses. And in particular, so there is many ways they do that, but one way that is going to be important for us is the way they generate stresses with actin in their cytoskeleton. So actin, it's a long chain of protein that has the shape of a fiber. And fiber of actin can be related by another protein that is called myosin. And this myosin is capable of extracting energy from outside world by doing some chemical reaction. That is really the pure biology we are not really interested in. And by that, extracting this energy, myosin is able to pull on the fiber of actin, and this is going to generate some internal stresses inside the tissue. So that's one important part that we have to take into account in our modelization. Another interesting and really quite funny thing is that cells are kind of smart. They can communicate one with another, and they tend to organize on a really larger scale. There is different kind of organization. You can have some nematic organization. If you think of the shape of a cell can elongate. And in general, in a tissue, the cells tend to orient their elongation in the same direction by some biological mechanism. So that's what we kind of a nematic organization. But the cells can also be polarized by some gradient of chemicals, for example, gradient of chemicals or protein inside of them. This gradient is giving you some direction. And also the cell, by communicating, try to orient this polarization to point on the same direction, for example. So on the mechanical point of view, this is important because this is making the tissue quite high anisotropic material, because the direction that to take the cells or the nematic organization of a polar organization is going to generate some anisotropy that you can see on the mechanics of the tissue. So you also have to deal with self-organization of the tissue, of the cells together. And the last point that is also important is that the tissue is able to feel its environment, its environment. For example, cell can be sensitive to gradient of chemicals in the outside world. They can be sensitive to gradient of stiffness of the substrate it's living on. It can also be sensitive to the curvature of that substrate. So sensitive mean, for example, cell can want to move in the direction of a gradient, or cells may want to elongate in this direction. There are going to be some cue that is going to affect the behavior of the cells and probably the mechanics of the tissue. So those are mainly the four original elements that you have to keep in mind and to put in your theory in way to model biological tissue. So now let me go to the project we are working on, the talk of today, that is about the rheology of blood vessels. So we worked with some postdoc that is now in Geneva, but that was doing her PhD at Paris in Ladix, and she just created some experimental setup that is able to mimic blood vessel, and we can control the pressure inside of it. So the way she did this is just to take some collagen gel, put some needle in the collagen, and take the needle back so that you have some cylinder inside of your gel, and you put the gel. You put some endothelial cells that are the cells that are forming the blood vessel, and they are going to proliferate. And at some point, the tissue is becoming a confluent, meaning that there is no more space in between the cells. They are covering all the tube. And inside of this tube, so the cells are forming a monolayer just like this. And inside of it, you have some fluid that is going to bring them some nutriments. And you can control the pressure of the fluid inside of the vessel. So you are able to control the pressure inside of this tube of endothelial cell that is kind of mimicking the blood vessel. So this is a picture of the experimental setup. So you see the cylindrical hole. It's something like 130 micrometer in diameter. And you see it's there. So you see it's much longer than its radius. And at the two extremities, you have the input of fluid and the output of the fluid. And what is nice with biology is that you always have some really nice and beautiful picture. You can do really, now with the optical method, you can do really nice imaging. And so by using those optical tools, they are able to really have the detail of the tissue. So you see there, this is your tube. So you see the monolayer, and you have all the cells constituting the tissue. So you see in blue the nuclei. You have in white the membrane of the cell. So you really have the detail of the biological elements of the tissue. So that's what is important, because we are going to impose some pressure, but also to see how those biological elements are going to respond to this change of pressure, not only the macroscopic change of the tissue. Okay, so now let's look at what is happening to the tube when we apply some pressure step. So you see here the gel, you see the tube there with the monolayer. So we don't really see the monolayer, it's here in white. And now, so you have some low pressure at the beginning, something like 200 or maybe 150 Pascal. And in a really small time, like 1 minute, we are going to go to 600 Pascal. And you see when you increase the pressure like that, you see some instantaneous increase of the radius of the tube. Okay, and if you record the evolution of the radius, so sorry, here it's much more the diameter than the radius, but okay. If you look at the evolution of the diameter with the time, so here you don't really see it on this curve, but you have this first elastic jump of the radius, and after that you see that after this instantaneous change of the radius, the diameter is still increasing. You have some quick increase at the beginning, and after some 7 hours, the increase starts slowing down, but still you have a continuous increase of the radius of the tube. So that's the macroscopic rheology of the blood vessel that we see. And to get a little bit more understanding of what is the behavior of the biological elements, you can have some image of the actin fiber that, if you remember, I was telling you that it's what is generating active stresses inside your tissue. So if you look, biologists have some way to isolate only one specific protein in their picture. So there they just image the protein that is called phalloidin, and that is the main component of actin. So you see that this actin is doing some kind of network of fibers. And what is interesting is that just before the increase of pressure, you see that those fibers are mainly orientating longitudinally, so parallel to the axis of the tube. But if you wait 7 hours after the pressure step, the step of pressure, what you see is that, okay, so mainly you see that the radius has increased, so this is not new. But you see that now the fibers are mainly circumferential. So they are normal to the direction of the axis. So you get some reorientation of the actin fibers during the time. And so if we quantify that, so in physics, we have some tools to quantify orientation. So we can construct some nematic tensor. So for people that are not really familiar, nematic tensor to be simple is just a matrix with a trace equal to 0. So here we constructed just by associating to each fiber a vector n. And if you do the product of n by itself, you get something that gives you some matrices. And due to the top bottom symmetry of the distribution, you have something that has no off diagonal coefficient. You only have one coefficient on the diagonal, and as it's a traceless matrix, it has to be the opposite on those two coefficients. So you are left with only one parameter, that is this small q, that is giving you an idea of the average orientation of the fibers inside the tissue. So I don't go. I think there is some.
Yeah, there are some questions, Nicolas. Yes.
Yeah.
Can I ask you? I'm very curious about the biological process in the sense, if I understood correctly, endothelial cells almost carry no load, right? Or they're very, very weak mechanically speaking, at least compared to the collagen. So the fibers that do the connection, the ones that you mentioned, well, the phalloidin, it is actively changed by the endothelial cells, and that's why we see this change of mechanics.
Yeah, so I'm going to speak about that when I'm going to present the model. But so with respect with the collagen, the endothelial cells are mechanically stronger than that. It's because of those fibers. So maybe by endothelial cells are not doing so much mechanically. Maybe you may say the membrane or something like that. But we have verified that it's not a response of the collagen gel that we see.
Okay.
If you do the same experiments, so it's not possible to do the same experiments without a layer of cells, because in this case you have some porosity of the gel and you can't apply a step of pressure. But if you do that and you kill the actin and you do the same step of pressure, you see a jump in the radius that is 2 times what you see if you have the actin. So this this really say you that it's the actin, or really the cell, the tissue that is responding to the deformation, to the step of pressure.
Thank you.
I think there is a second question.
Yeah,
by
Dr. Ashif.
Ashif
go on.
Akram.
Nicholas, I have a question.
Yes.
This actin orientation is basically in a plane. Is it like a single plane?
Okay,
Because
so you have your tube, and you have to. It's a projection of the tube on a plane, but it's really it's not it's not a cross section of the tube. It's really a projection of all the left part of the tube.
on the left part of the tube on a plane, and the plane is what is the orientation of the plane? The
So
projection.
okay, so you see the tube is like that. You have the axis of the tube.
Yeah.
On the plane, yes, it's so here it's the bottom, here it's top.
Is it like
Yeah.
XZ
Yeah.
plane?
You can say it
Like 9. Okay. Okay. And
But it's really a projection. It's not a cross section of the tissue. What you see is really the curve.
right. This is basically the experimental outcome of what you are saying. Saying, right? Basically the experimental measurement, and that's being done with projection. Okay.
Yes.
Okay, that I understand. But what I'm a little bit hesitant about is why it's coming out to be simply delta is. Is that Kronecker delta?
Yes, it's a connector. Sorry, I could have do this a little bit simpler. Yeah, it's just this part is just to say that you make this product traceless, Because if you do just the average of the product of the component of the vector n, you are going to end with something that has a trace. So to make it traceless, you just subtract 1/2 the identity to that.
And why are you making it traceless? Because you want to just find out that
It's the way of doing. You can have it with trace, but the trace is not giving you so much information. And by making it traceless, you have only one parameter that is left, and that is measuring the average orientation. So in general, when people want to deal with orientation of something in physics, they use this kind of a nematic tensor. They make it traceless. It's simpler. It makes the calculation simpler in general.
Yeah. And the way I imagine is basically the trace, the delta Ij by 2. That part is basically like preferred orientation, and this is Qij basically measuring the deviation from the preferred orientation. Is that physically? Is that the correct picture?
Qij is measuring what? I didn't get it.
What I imagine is it's basically giving you the deviation from a preferred orientation or some kind of standard orientation.
No, it's really giving you the preferred orientation, and the Q equals 0 mean that you have an isotropic distribution of fibers. Okay, so Q equal to 0, you have all the direction that are equally distributed. And the absolute value of Q has to be less than 0.5 by construction. And if it's negative, it tells you that the fibers are mainly orientating along the axis of the tube. If it's positive, it tells you that the fibers are mainly orientating circumferentially. And if it's minus 0.5, it says that all the fibers are really strictly parallel to the tube of the axis. On the plus 0.5, it's saying that all are aligned in the same direction, but circumferentially. So it's giving you some information about what kind of direction of preferred direction the network has, and what is the alignment of all the fibers together. Okay. I hope it's clear for everyone. Okay, so you see, if we plot that for different time of point, so time 0 is just before the step of pressure, and after that 7 is 7 hours after the step of pressure. Okay, so you see that you have some quick reorientation of the fibers that in less than 7 hours become circumferential, starting with some longitudinal preferred orientation. Okay, so that's what experiments tell us. And we can look at another protein that is cadherin. So cadherin is a protein that is linking the cells together. So the green line that you have there is actually the membrane of the cells. In blue, you have the nuclei, but our model. But so you see that the cells are really elongated. It's not a simple circle. It's really like elliptical or kind of elongated shape. And at the beginning, just before the step of pressure, they are elongating much more in the longitudinal direction. But once again, if you look 7 hours after the step of pressure, you see that the orientation of the elongation has changed. So with both the picture, we can look at different quantity for the cell. We can look at the cell average area. So you just look at this cell, for example, and you look you calculate the area. You do that for all cells, and you divide it by the number of cells, and it gives you some average quantity. That is the average cell, the average area that a cell in the tissue have. So you see, once again, just before the step of pressure, you are somewhere there. You see some increase of the area of the cell at the beginning. So it's normal because you are inflating the tissue, so the cell on that are getting more and more area. But at the end, you see that you have some drop of this cell average area. This is because you have cell division, and at the end, the cell division is winning the game. And the cell division is much much quick. Yes, it's much quick than the expansion of the tissue, so the area is reducing. And also, if you look at so you can define some nematic tensor for the orientation of the cell elongation, and you will see just as for the orientation of actin, that this orientation, mean orientation, is longitudinal at the beginning, and in less than 7 hours it reorientates. But you see that it's also dropping at the end. It's going to zero, meaning that at the end the cells are going to become isotrope again. So those are going to be like circles. So at the end you have small circles because you have small cell area on the isotropic elongation. Okay, so those are the experimental observation that we have, and now from that we want to build some mechanical model in order to reproduce all what we see. So we model the vessel just as a tube, an infinitely thin tube of radius r, and with a length L that is going to be constant. And we do some average theory. We are not looking at the mechanics locally, but we really look at it in average. So the mechanical equilibrium of that is really simple. It's what we know as the Laplace law. That is just the equilibrium of force, the force balance in the normal direction. That say that the tension. So tension, it's a 2D stresses for those who are not familiar with this notion. It's just like stresses, but in a 2D material. So the tension inside the tissue has to equilibrate with the pressure, with some contribution to the contribution of the radius of the tube. So the radius times the pressure has to be equal to the tension. It's the simple mechanical equilibrium of this tube. So this is quite simple, but now we have to determine what is generating tension inside the tissue, and that's the hard part of the modeling. It's really to determine and to get the good form of the good constitutive law to say what is generating tension and in which way. So looking at the experimental observation that I show you, we have 3 potential candidates that can generate tension. You can have some cell area elasticity, meaning that all cells have a preferred area, and when you stretch them, they want to go back to this area, or if you compress them, they want to go back to this area by generating isotropic tension. So this is this first term. You can also have elongation elasticity. So maybe that the preferred state of cell is an isotropic state where the cell is a circle. And when you create some elongation in the cell, it wants to go back to this reference state, this isotropic state, by generating some tension in the direction of its orientation. And you also have the actin, as I said you, the actin, we know it's an important element for active stresses. So we can also have some contribution of the actin. So we have 3 possible candidates, but we can cancel some of them, because if you look at the Laplace law, it tells you that for constant pressure, and we are working at constant pressure, if the radius is increasing, the tension inside the tissue also has to increase. And you see that the radius is continuously increasing, so the tension in the tissue has to increase. But if you look at the cell average area, you see that at least a long time you have a drop, and it becoming even smaller than at the beginning. So it means that a long time, this term can't participate to the tension. It can't explain what is happening there. Just the same for the elongation. You see that at the end you have no elongation, but still you have an increase of tension inside the tissue. So it means that at least at long time, the elongation of the cells are not playing an important mechanical role. So it left us with just the last candidate, that is the actin. Okay? So that's why we started just by saying, okay, actin is generating the tension inside of our tissue, and with all the parameters that we are measuring, only the orientation of actin is important in the mechanics. So how can we modelize the tension generated by a network of actin? So we suppose that a fiber of actin is only generating tension in its direction. It's only pulling in its direction and generating tension in this direction. And that, because of that, if you take a network of actin fibers, this network is going to generate a tension only in its average direction. Okay, so that's why now we have to add some tensor that is similar to the identity to have some trace to have tension only on the direction on the mean direction. So you have here the direction of the actin, and you have here some coefficient that is the active tension coefficient of the actin. So actin is generating some kind of active tension in its direction. But you see that if this coefficient is constant, you are again going to have some problem, because the orientation of the actin is plateauing at some point. At long time, it's plateauing, it's not evolving. So if this part is constant, as we say, the tension has to increase because the radius is increasing. So this part, the tension that is generating by the actin in its mean direction, also has to increase.
We have a question from Pablo.
Yeah.
Yeah.
Yes.
Oh, yeah.
Pablo.
Maybe I just misunderstood something, but in the experiment, when you ramp up the pressure, is it just hydrostatic pressure, or is it actually a flow moving constantly through the pipe?
There is a flow moving constantly, because you have constantly to bring some nutrient to the cell. So you always have a small flow, but yes, you have a flow. But I think that the shear generating by this flow is negligible with respect to the pressure that you have inside of it.
Perfect. That was my question. Thanks.
Okay. Okay. So yes. So now we have to add some complexity to the description of the tension generated by actin, because it has to respond to the deformation. So there is a lot of choice that we can do at this point. We try to modelize it in quite a simple way. So we just say that, okay, the actin is generating some active tension that we call zeta 0. And this is a constant, and this is going to be always constant, and it's going to generate to apply this tension in its main direction. But we consider that actin also has some elastic response to deformation. So in a kind of a rheological modelization, you can just see it as a spring in parallel with some constant tension. Okay. And so you have some strain variable. You have to measure the strain, the elongation of the actin. That is going to give you the tension, the elastic tension generating by the actin. And for that, we consider that, once again, the orientation of the fiber is important. If you consider a fiber and you stretch it orthogonal to its direction, you are not going to stretch it at all. You are not going to elongate it, so you won't have any elastic response of the fiber. In the contrary, if you are stretching it in the direction of its orientation, you are going to have an optimal elastic response of the actin. So the way actin fibers are stretched is taken into account of the alignment of the fibers with respect to the material flow. So if the fibers are orthogonal to the material flow, there will be no elastic response at all. But if it's orientated with this deformation, it is going to be optimal in its response. It is going to resist to the deformation. And in between, it's intermediate. Is it clear, this part? I hope.
Yes, it is. It is pretty clear.
So, well, we can say we are done with that, but actually we have some more experimental data that I didn't show you yet. Is some kind of experiment that are really cool and that biologists like to do to have some measurement, really local measurement of the tension in tissue. So some of you may know, maybe it's what we call laser ablation. So if you have a tissue with some laser microimpulsion, you are going to cut it in a really do a line that you can align in the direction that you want. So you can do some longitudinal longitudinal cut, and you just see the tissue, the response of the tissue to this cut. If the tissue is under tension, the cut is going to open. Okay, and the more tension you have, the quicker it will open. The more will be the velocity of the opening of these cuts. Okay, so by doing cut in different direction and looking at the velocity of the opening of these cuts, you are able to have some kind of measurement of the tension that you have in one direction. So if you do a longitudinal cut, you have some idea of the circumferential tension. And if you do some circumferential cuts, you have some idea of the longitudinal tension that you have. Okay. So when we do that, just before the step of pressure, so when we are at 150 Pascal, and just after the step of pressure, we see some differences. So if you do cut in the two direction just before the step of pressure, you see that you have the same amount of tension in the two direction. You have some isotropic tension. You don't have any anisotropy in the tension. But if you do it just after the step of pressure, you see that now you have much more tension in the circumferential direction. Okay. So the amount of tension in the longitudinal direction is almost the same than before, but you have a big increase in the circumferential direction. And with if we consider that there is only actin that is generating tension, this is a problem, because the way we model the actin generated tension is that actin is generating tension in its direction. And we know that just after the step of pressure, actin did not reorientate immediately. It's still longitudinal. So just after the step of pressure, the actin is not circumferential, and it cannot explain this increase of the circumferential tension there. So it means that there cannot be just this actin generated term there in our constitutive law for the tension of the tissue. So there is something else that mainly we are not measuring, because I said you that the elongation of the cell area can be the explanation for a long time rheology of the tissue. So there is something else, and we suspect that this something else is really the cohesiveness of the tissue. Because if you look at the tissue, okay, you have cells that are linked one with another. So there is some protein in between the membrane of each cell that is linking all the cell together. And inside the cell, you have the cytoskeleton, so mainly the actin fibers. So you see that, okay, even if all the fibers are directed longitudinally, if you stretch this tissue in a direction that is orthogonal to the direction of the fiber, still you should have some response to some resistance of the tissue because of those junction in between the cell. But we don't have experimental data for that, so it's a kind of assumption that we do in our model, is to add some tension contribution coming from the rest of the tissue, whatever is the rest. It can be, as I said, the junction in between the cells. It can be over the cytoskeleton. We don't really know, but we know that we need that to explain this anisotropy of tension. And for this additional parts, for this additional tension, we choose some simple Maxwell fluid, isotropic Maxwell fluid model. So in tensorial formulation, this gives you this, but it means that if you deform in one way, the material don't care about any orientation. It is just going to respond in the same way. Okay, but as a Maxwell fluid, so with a short time elasticity and a long time viscosity. And the long time viscosity is really important because if you don't have any long time viscosity, if you stretch the tissue, you will have the elastic response, and after that you have the fiber of actin that are reorienting. So they are generating more and more tension in the circumferential direction. So you should see the tissue, the tube that is shrinking. So as it's not shrinking, it means that this tension that is responsible for the anisotropy of tension has to relax at some point. So that's why we take some Maxwell model there. Okay, I hope it's still clear.
I do have a question.
Yes.
Do you have some polydispersity of your fibers or not? And if so, if you have some polydispersity, does it play a role in your stretching or not?
Is it polydispersity in the size of the fiber?
Yeah, exactly.
Yeah, so yeah, we have polydispersity, but we assume that the size of the fiber is not really important in the stress that is generating, because it's just like a rod that you are pulling, and whatever the length of your rod, what is important is how strong
like the direction
you are pulling on the rod. So we don't take into account the polydispersity.
Okay, doesn't change the modulus.
We only take into account the direction of the fiber.
Okay.
You have some polydispersity
of the direction, of course.
Orientation, but it is taken into account because we take the average direction.
Okay, thank you.
Is it okay?
Yeah, perfect. Thank you.
Okay. So now we are done with the constitutive relation for the tension inside the tissue. We only need one last element to complete our model, is what is doing actin, how actin is moving, how actin is acting. So as I said, you have some reorientation of the actin fibers. So we have to understand what is driving this reorientation. So first we thought that maybe it's only the deformation. As you are stretching in one direction, if you are stretching a material, you are going to advect the fibers, and this may be explaining the reorientation of fibers. So to be sure or not, if it's really this passive geometrical effect, what we did is just to take a picture just before the step of pressure, and artificially stretch it in this direction, in the y direction. So you get this picture, the blue one. But this is just the stretch picture of this one. And we compare with the real picture at the same rate of deformation. So the dash line is the experimental data that we have. And you see, if you look at the same deformation, at the same increase of radius, you see here the artificially stretched picture, and here the real picture. And you see that the fibers are much more oriented, circumferentially oriented. That's what you get with some geometrical reorientation. So this means that you need something else to reorientate the fibers. It cannot be only the material flow that is reorientating the fibers. So we choose some equation for the dynamics of actin. So we write some dynamics on the mean orientation tensor of actin, and we take into account two effects in this dynamics. So the first one is that we consider that the actin is a nematic phase, so meaning that all the fibers want to point in the same direction with a preferred alignment, that is a Q0. So if Q0 is 0.5, it means that all the fibers want to be every time perfectly orientated. D'accord? If it's 0, it means that they don't care and they can be just isotrope. So the value of Q0 is giving you the magnitude of the preferred alignment of the fibers. And the second term is the sensing term. Okay, so based on what people know about actin, we suspect that actin is sensible to tension, and actin may want to reorientate in the direction of the anisotropy of tension. So we put some tension alignment term there that make the fibers reorientate with the tension, the anisotropy of tension in the tissue. So here, if you see, you have this TR. So I just remember what is TR. Remind you what is TR. TR is the tension generated by the rest of the tissue. Okay. Here we could have put the total tension in the tissue, but the problem with the total tension, when you put it, it's working well. There is no problem in reproducing the data. The problem is much more physical. If you put the total tension in the tissue there, it means that the actin is sensing its own tension and want to reorientate in this direction. So if you have actin in the tissue where you have only actin generating tension, it means that they always want to be in the direction that they already are. So this is not really physical for us. So that's why we prefer to take this coupling with the tension in the rest of the tissue. Okay, so with that, now we have some kind of explanation for what we see. Okay, we just simulate that and fit the parameters of our model in a way to reproduce the experimental data. So you see there the evolution of the radius there. So in red, the red dots are the experimental point that we have. And the continuous red line is what is predicting our model. So you see we are not so bad. And also we did the same for the mean orientation of actin. And once again, we capture the orientation of actin not so bad. If you look at tension, so you have in red the tension in the circumferential direction, in blue the tension in the longitudinal one. So you see that just before the step of pressure, well, you are not as isotropic as we see with laser ablation, but still the tension are quite close. But just after the step of pressure, you see that you have a big increase of the circumferential tension that reproduce the experimental data that we see from a laser ablation, and we see that the increase in longitudinal tension is quite small with that. So we are not so bad with the experimental data that we have in our possession. And now we can try to understand with this model what is happening. So before the step of pressure, you have a small pressure in there. Okay, the actin fibers are mainly orientating along the longitudinal axis of the tube. Okay, and you have a small tension, small circumferential tension. And once you apply your step of pressure, as the actin is rotating in the direction of the tube, it's not responding in an optimal way to the deformation of the tissue. And it's mainly the rest of the tissue that is an isotropic Maxwell fluid that is going to elastically respond to this increase of pressure. So that's why if you look at the beginning, so you see here in red, you have the full tension inside the tissue. In green, you have the tension that is generated by the actin. And in the dot line, you have the tension that is generated by the rest of the tissue. And you see that just after the step of pressure, it's mainly the tension in the rest of the tissue that is increasing and that is responding, contributing to the response of the tissue. You see the actin is almost continuous. You almost have no jump, no elastic jump in the tension of the actin. But after that, so you generate some tension in the rest of the tissue. And as I said, in our model, the actin is sensitive to this tension. So now the actin want to reorientate in the direction of this tension. Okay, so now the actin start to reorientate to become circumferential. But as this the tension in the rest of the tissue is viscous, it is going to relax at the end. So it's what you see on this curve. You see that the tension in the rest of the tissue is relaxing. But in the same time, the actin become more and more aligned with the deformation and responds more and more strongly. So you see that at the end, you reorientate the fibers of actin that are now in the good direction to resist to the deformation of the tube. And they are now responding elastically to the deformation and prevent the tube to inflate too much. So that's the physical image that we have, how the tissue is able to preserve its integrity. You see, for example, if we play with the behavior of actin, so here in blue is what we get if we block the reorientation of actin with tension. So you see the actin is going to stay always in the same direction, and we won't reorientate it. And you see in blue, you see the curve in blue in the radius, it's going to explode. So if you it's really important that actin reorientate to resist to the deformation. Otherwise, you just have a fluid that is under pressure, and of course, it's exploding. And also in green, you have what happen if you now suppress, cancel the elastic behavior of actin. You only have actin stress, active tension. You see that once again you are not able to resist to the deformation of the tissue. So the behavior of actin is really important. And I think I'm quite on my time.
Yeah, it's perfect.
Yeah,
Just
so I will
one sec, I'm sorry for the sound.
I will just conclude by going back to this slide that I show you in my introduction. I said there is 4 main elements that we have to take into account to model tissue, biological tissue. So I said there is geometry, activity, self-organization, and environment sensing. And now I would like to show who is where in this model. So the geometry is just by writing the mechanical equilibrium for a tube. So we take it into account by taking a cylindrical geometry and applying the Laplace law that is related to this cylindrical geometry. So this is quite simple. The active parts, so it comes from the actin, and we said that actin generated tension as some part that is some constant. So this active parts. It means that actin with the help of myosin is extracting energy from its environment and generating some constant tension in its direction. So here is the active part of our model. Self-organization, once again, is about actin. And we say that actin is in a nematic phases. So actin fibers want to point in the same direction. So that's this term in the dynamics of actin. And the last one, so the environment sensing. So I said there is a lot of kind of environment sensing. And the one that we chose there is a sensing of the tension inside of the rest of the tissue. So it is this term. All with that, we have the 4 original terms that make some nice biological tissue continuous theory. And I think that I can stop there.
Yeah.
If we are on time.
Thank you,
If there
Nicolas. It was a really nice
some
talk.
question.
Thank you. Is there any question in the audience? Yeah, Sean, you can ask your question. Oh no, it's not a question. It's like a clap, like bravo. Oh yeah, Tammy, you can ask your question.
Okay, I think Tammy.
Thank you, Nicholas. Can you hear me okay?
Yes, the sound is a little bit small, but okay.
Can you hear me now?
Yeah, now it's okay.
Good. Really enjoyed your talk. Thank you for that. Just a very technical question. Actually, you introduced at the beginning that you basically got a pressure head and then a downstream lumen pressure. What kind of wall shear stresses are you getting in there? I may have missed it.
The wall shear, you mean? Okay, so I think it was the question of Pablo previously. There is some shear that is due to the fact that there is some flow inside of the tube, of course.
Yeah. What kind of values do you have?
The value,
Do you know? Yeah.
actually, the people we collaborate with measure it. So Claire measure it in its PhD, but I don't have the value in mind. I don't remember it, but it's
Okay. I was just
kind of
curious what
usable.
sort of what magnitude you were at.
If you want the answer, you can email me, and I will find I will find it. We have it somewhere, but I don't have it in mind.
Beautiful. Okay. Thank you.
I think there is
Thank you, Lydia. Lydia, you can ask your question.
Hello.
Hello?
Hello. Am I audible?
Yes.
Yeah, perfect.
Okay, so my question is regarding, so we know that usually actin and myosin, they work together for muscle contractions and stuff like that, right?
Yes.
So here, when you're considering the fact that, actin is taking energy from, the environment and doing whatever, so do you consider the effect of myosin together with it, or because it's like different thicker filaments, right? Myosins are. So
That's a really good question. Yeah. Because actin by itself is not generating tension. As I said, it's really the combination of the two, of actin with myosin, that's generating tension. But the fact is, okay, so we can imagine what we want in a biological system. But our collaborators didn't image the myosin, so we don't know really what is doing in myosin. But for sure, there is myosin. But for example, when I said we have some problem there because this coefficient can be constant. Something maybe that there is more and more myosin, and this coefficient is actively increasing. But it's a way that we didn't choose because we don't have the data for myosin. But of course, it's not actin by itself that is generating the tension. It's really the complex of actin coupled to myosin.
Right. Okay. Thank you. Thank you.
Is there another question?
It was really, really interesting. Don't hesitate to send question also. I'm pretty sure that Nicolas can answer to you right away by email. Yeah.
If you're interested in whatever I said, you can mail me. We have some preprints in bioarchive about that if you want to really have all the details. You can also look at it.
Thank you so much. Thanks again, Nicolas. It was really a pleasure to have you to talk for this hitchhiker guide to rheology. Michelle, I don't know if you can hear me, but you can send the slides. Oop. Thank you, Michelle. So thanks again, Nicolas, for your talk. And next week, we're going to have a class from Frédéric Restagnot, who's a researcher at Université Paris-Cité. and he's going to talk about Navier-Stokes binary condition, sleep of liquids. And yes, see you next week. I'm gonna stop the recording now, and we can, for some of you, we can share some stuff. Bye bye everyone. I'm gonna stop the recording now, and sorry again for the whole sound behind me.